Dear students, after studying this module, you shall be able to understand the basic concept of nitrogen, fluorine and phosphorus NMR, know about the internal and external standards to record these spectra, know about the heteronuclear coupling between nitrogen, fluorine and phosphorus atoms. Now students, let us begin with the 15 nitrogen NMR spectroscopy. The 15N NMR spectroscopy is employed to determine the structure of nitrogen containing compounds. Nitrogen, as you know, has two isotopes, that is 14 nitrogen and 15 nitrogen, and both are NMR active. 14 nitrogen has a nuclear spin of 1, whereas 15 nitrogen has a nuclear spin value of 1/2. The natural abundance of 14 nitrogen is 99.63%, which is much higher than 15 nitrogen, which has an abundance value of 0.37%. Since 14 nitrogen has an integral nuclear spin, that is I is equal to 1, I being the spin quantum number, and thus it possesses quadruple moment and its signals are usually significantly broadened by quadruple relaxation mechanism. Now sometimes the broadening of the signal is to the extent that they are not observable on a high resolution NMR spectrometer. Now the other isotope, which is the 15 nitrogen, that has a spin of 1/2 and no quadruple moment, but it is only 0.37% abundant and hence it is very insensitive. Sensitivity is made worse by its low gyromagnetic ratio, which has a value of -27.126 into 10 to the power 6 Tesla inverse second inverse, which is 10.14% that of one hydrogen, that is proton. The signal to noise ratio for proton is about 300-fold greater than 15 nitrogen at the same magnetic field. Now here in this figure you can see the comparison of 14 nitrogen and 15 nitrogen spectra of urea. The 14 nitrogen signal is broader due to quadruple moment. The extent of broadening depends on the molecular structure. Larger the molecule, more asymmetric the nitrogen's environment, broader is the signal. Hence, the small and highly symmetric aqueous ammonium ion gives a very sharp line, that is less than 1 Hz widening. Liquid ammonia, being less symmetric, is 16 Hz wide. Urea is larger and asymmetric, so the line width is approximately 1 kHz. Molecules that are significantly larger than urea yield signals too broad to be observed. This you can see clearly in figure as I have explained you just now. Now let us come to other aspect. With highly sensitive instruments and making maximum use of various signal enhancement methods like DEPT, depth, NOE, natural abundance spectra can be recorded for 15 nitrogen. The advent of new techniques such as pulse sequences and polarization transfer in conjunction with the use of high field magnets and large sample probe heads largely solved this detection problem. Now chemical shifts of nitrogen nuclei cover a wide spectral range of about 900 ppm for most organic and inorganic compounds. There is no measurable isotopic substitution effect on the chemical shift value. Hence, 15 nitrogen and 14 nitrogen shifts may be used interchangeably. Various standards, internal or external, have so far been employed as references for nitrogen chemical shifts. There are two different types of chemical shift scales in 15N NMR. IUPAC, that is International Union for Pure and Applied Chemistry, recommends nitromethane for the chemical shift reference to be recorded as a reference, and its value, just like TMS in the proton and carbon spectra, must be 0 ppm. However, some people also use liquid ammonia. For 15 nitrogen, chemical shifts referenced with liquid ammonia are 380.5 ppm upfield from nitromethane, that is delta for ammonia is equal to delta for nitromethane plus 380.5 ppm. The heteronuclear coupling with 14 nitrogen is rarely observed because of its quadruple broadening. It can be observed only when nitrogen atom is quaternary, like in ammonium ions, at room temperature and liquid ammonia at low temperatures. Two bond coupling for nitrogen 14, like 14 nitrogen dash CO2, that is single bond CO2, are not observed even when the nitrogen is quaternary, presumably because the coupling is very small. The proton spectrum of natural abundance of ammonium chloride, which is a 1.5 molar solution in 1.5 molar HCl in water, showing a coupling to 14 nitrogen, which has a spin quantum value of 1 as a triplet. The 14 nitrogen spectrum of similar ammonium chloride, which is again 1.5 molar in 1.1 molar of HCl H2O, it shows a coupling to proton as a quintet, that is 4 protons present at nitrogen atom. Now you can appreciate the difference that I have told you. Now students, let us shift our focus from 14 and 15 nitrogen to 19 fluorine NMR spectroscopy. Now 19F NMR is used to analyze the structure of fluorine containing compounds. Now 19 fluorine is the naturally occurring isotope of fluorine with 100% abundance. It has a nuclear spin of 1/2 and a high gyromagnetic ratio, which means that this isotope is highly sensitive to NMR spectroscopy. Because of its favorable nuclear properties and high abundance, 19F NMR spectroscopy is highly sensitive and fast as compared to proton NMR spectroscopy. Indeed, the 19F nucleus is the second most receptive NMR nucleus after proton nucleus. Now, the 19F NMR chemical shift range is very wide, that is from 0 to 200 ppm, as compared to that of proton NMR, in which the range is 0 to 15 ppm only. The reference compound for 19 fluorine NMR is trichlorofluoromethane, that is CFCl3. It is generally inert, volatile and gives rise to a single 19F peak at delta value of 0. When measurements are done at the same radio frequency, the signals from 19F absorptions occur at considerably different magnetic field strength than that of proton. Thus, one does not see the peaks due to 19F absorptions in proton NMR spectrum. However, students, the peaks due to the proton can show splitting due to spin-spin couplings between protons and 19F nuclei. The figure shows the chemical shift range for the fluoroorganic compounds. The most commonly encountered signals arising from organofluorine compounds generally lie between 50 to 70 ppm, that is for the trifluorocarbon groups or the CF3 groups, and between 200 to 220 ppm for CH2F groups. The very wide spectral range can cause problems in recording the spectra of 19F NMR, such as poor data resolution and inaccurate integration. Now, as you can see in this figure clearly that the chemical shift for the fluoroorganic compounds is seen here as I have explained you before, and you can see the ranges of all sorts of organofluorine compounds in this figure. Now students, considering the multiplicity of the peaks. The multiplicity of the peaks gives the information about the neighboring atoms to the fluorine. The coupling constants between fluorine nuclei are generally larger than those for hydrogen. Germinal fluorine-fluorine coupling ranges are from 40 to 370 Hz and vicinal fluorine-fluorine range from 0 to 45 Hz. The cis-vicinal coupling ranges are from 0 to 60 Hz and the trans-vicinal coupling ranges from 100 to 150 Hz. Now, long range coupling more than 5 bonds is having very low value of 0 to 18 Hz for the coupling constant. Now, let us come to coupling between hydrogen and fluorine, which is very strong. Coupling between hydrogen and fluorine nuclei is also very strong. Geminal coupling ranges from 40 to 60 Hz and vicinal coupling ranges from 1 to 30 Hz. The cis hydrogen fluorine coupling constants range from 0 to 20 Hz and the trans coupling constant value range is from 10 to 50 Hz. Fluorine attached to benzene also couples with protons on the ring. The coupling constant values for ortho, meta and para ranges from 7 to 12 Hz, 3.5 to 8 Hz and 0 to 3 Hz respectively. Now students, in figures you can see the fluorine and 19 and the proton NMR spectrum of 1-bromo-1-fluoroethane, telling you the formula CH3CHFBr. Each spectrum is recorded using a 1.4 Tesla magnet. In the proton spectrum, the hydrogen-hydrogen coupling between CH3 and CH protons should give you a quartet and a doublet, but the HF coupling complicates the splitting pattern. The methyl signal is further split by 19F. Each line of the doublet is split into 2 by the large vicinal hydrogen fluorine coupling, whose coupling constant is 22 Hz. The methyl signal therefore appears as a double doublet. The CH signal is split into a quartet by methyl, whose coupling constant is 6 Hz, and then each line is further split into a large geminal hydrogen fluorine coupling, whose coupling constant is 50 Hz. The CH signal is therefore appearing as a doublet of quartets. In the 19F spectrum, the fluorine signal is split into a doublet by the geminal methine proton having a coupling constant of 50 Hz, and each line is further split into 4 by the vicinal methyl protons having a coupling constant of 22 Hz. Thus, peak due to fluorine is an overlapping doublet of quartets. You can clearly see this splitting in this figure showing the proton and the 19F NMR spectrum of 1-bromo-1-fluoroethane. Now, let us consider figure which shows the 19F NMR spectrum of 1-bromo-3,4,5 trifluorobenzene. There are 2 sets of fluorine atoms in this. The fluorine atoms at the 3 and the 5 positions are chemically different from the fluorine atom at 4 position, Now consider F3 or F5, both the nuclei couple with the adjacent F4 nucleus to give a doublet, which further splits into a doublet by the neighboring proton to give a doublet of doublets. The fluorine F4 will couple with the two equivalent fluorine nuclei F3 and F5 to give you a triplet, and also with the two chemically equivalent protons. Therefore, signal due to this fluorine appears as a triplet of triplets. Now you can clearly see the signals as I have described to you in this particular figure, where you can see the F19 spectrum of 1-bromo-3,4,5 trifluorobenzene. You can clearly see the splitting and you can demarcate which proton and which coupling it is. Now students, we shall consider the NMR spectroscopy of 31 phosphorus. Phosphorus 31 NMR spectroscopy is used to identify the phosphorus containing organic and inorganic compounds. It is commonly found in organic compounds and coordination complexes. Few examples are phosphines, phosphides, phosphonium salts, nucleic acids containing the phosphate esters, and also other important biomolecules such as ADP, that is adenosine diphosphate, and ATP, adenosine triphosphate, etc. It is one of the more routine NMR techniques, as 31 phosphorus has an isotopic abundance of 100% and a relatively high gyromagnetic ratio, which is 40.5% of that of proton. Like proton and 19F, that is 19 fluorine, it has a spin of 1/2, thus making spectra relatively easy to interpret. Now 85% phosphoric acid, that is H3PO4, is conventionally used as an external standard, which is assigned the chemical shift of 0. The chemical shift ranges of phosphorus are from 0 to 250 ppm and is much wider than the typical proton spectrum NMR. Now 31 phosphorus shows an interesting pattern in coupling with the neighboring atoms. The size of the coupling normally decreases dramatically with the number of intervening bonds. A proton directly attached to phosphorus, that is PH3 in phosphine, is split by a large coupling constant, that is one bond coupling of about 600 Hz. Thus, the two components of a doublet will be far apart from each other, that it would normally not be accepted as a coupling. The two bond coupling, that is in triphenyl phosphine CH2, are comparatively smaller, that is having a coupling constant of 20 to 30 Hz, while 3 bond coupling of triphenyl phosphine CH2CH2 ranges from 5 to 10 Hz, and 4 bond coupling, that is PH3P, that is triphenyl phosphine CH2 whole thrice, is very small and the coupling constant is less than 1 Hz and is rarely observed. Like 13 carbon spectrum, 31 phosphorus spectra are recorded with proton decoupling. In 31 phosphorus NMR spectrum of triphenyl phosphine, it shows a sharp singlet. This you can see the figure. If the decoupler is turned off, the 31 phosphorus peak will be observed as a multiplet or a broad peak due to the coupling with ortho, meta and para protons of the phenyl ring. Now students, let us concentrate on figure which represents the 31 phosphorus NMR spectrum of diethyl phosphonate with proton decoupling and showing 1 bond and 3 bond coupling between 31 phosphorus and 1 hydrogen, that is proton. As you can see here, the figure shows the 31 phosphorus NMR spectrum of diethyl phosphonate. You can see in A, that is part A of the spectrum, the hydrogen has been decoupled, and in part B of the spectrum, the 1 bond and the 3 bond coupling with hydrogen. Now let us come to another figure which shows the 31 phosphorus NMR and proton NMR spectrum of a square planar complex, that is MH triphenyl phosphine whole thrice. There are two different sets of triphenyl phosphine group in this complex. The two triphenyl phosphine groups shown in blue color are equivalent and the one shown in red color is different. Hence, in the 31 phosphorus NMR spectrum, two sets of peaks will be observed. The red phosphorus nucleus will couple with the two equivalent blue colored phosphorus nuclei and will give a 1:2:1 triplet. Similarly, the blue colored phosphorus will couple to the single red phosphorus to give a doublet. The coupling constant JPP, PP in the subscript, will be the same in both the cases. It is important, students, to note here that the coupling between phosphorus and hydrogen in this spectrum has been removed by the decoupler, and all the coupling is phosphorus-phosphorus coupling only. Now students, you can appreciate more by looking at the figure. The part A of the figure or the spectrum shows you the 31 phosphorus NMR, whereas part B shows you the proton NMR spectrum of square planar complex signals due to aromatic protons which have been removed in the proton spectrum. So, you can only see the proton spectrum of square planar complex. Now, consider the proton NMR spectrum. The hydrogen in the actual hydride attached to the metal will couple to the red triphenyl phosphine to give you a doublet. This hydride will also couple to the two equivalent blue triphenyl phosphines to give you a 1:2:1 triplet. The first doublet splitting would be larger than the second triplet splitting, that is coupling between trans-oriented nuclei is usually larger than the cis ones. Thus, the signal for the proton will be observed as a doublet of the triplets. The phenyl protons in the molecule are far away from the hydride atom. Hence, coupling will not be observed with the aromatic protons. Now, let us note some important points here about this 31 phosphorus spectra. The hydride atoms attached to the metals appear at the extreme right, that is in the negative ppm values in the proton spectrum. In the present case, from -4.76 to -5.24 ppm. There will of course be some signals for the phenyl protons near 7 ppm in the proton spectrum with an integral value of 45 protons. 3 triphenyl phosphine is equal to 9 phenyl rings, each with 5 protons. Now you can see when 31 phosphorus is attached to the hydrogen atoms, how in the hydrogen spectrum the values of delta are going to change, and this I have told you in the important note as I have stated. Now students, let us summarize this module. Nitrogen has two isotopes, that is 14 nitrogen and 15 nitrogen, and both are NMR active. There is no measurable isotopic substitution effect on the chemical shift value. Hence, 15 and 14 nitrogen shifts may be used interchangeably. Now, 19F is the naturally occurring isotope of fluorine with 100% abundance. Phosphorus 31 NMR spectroscopy is used to identify the phosphorus containing organic and inorganic compounds. The 31 phosphorus has an isotopic abundance of 100% and a relatively high gyromagnetic ratio, 40.5% to that of proton. Like fluorine and proton, it also has a spin of 1/2, thus making the spectra relatively easier to interpret. Now, I hope students you have found this module very informative regarding the 14 and 15 nitrogen and 31 phosphorus and 19 fluorine NMR spectroscopy.